Now we're going to look at the ideal gas law. Now an ideal gas is one that follows all the gas laws with all the conditions of pressure and temperature and volume. Now really there's no such thing as an ideal gas, but at most or many conditions of temperature and pressure, real gases behave like ideal gases, so that's why we can use this law, the ideal gas law, to calculate many of these different things. The ideal gas law does not work, or it will differ from a real gas at very low temperatures or very high pressures. But really between that, if we're not having high pressures or very low temperatures, we can use the ideal gas law. What is the ideal gas law? It's PV equals nRT. P is pressure, of course, what we've been using before. V is volume. And a new one is moles. And T is temperature, has to be in Kelvin again. Now R is the ideal gas constant. Now it's always going to be 8.31 liters, which is the unit for volume, kilopascals, which is the unit for pressure, and Kelvin mole. So Kelvin temperature and then moles would be in mole. So using this formula, we can solve many problems. The ideal gas law. So if we have this problem, how many moles of gas does it take to occupy 120 liters at a pressure of 230 kilopascals and a temperature of 300 K? So what we're going to do is write down everything that we're given. So the volume is 120 liters. Pressure is 230 kilopascals. Temperature is 300 K. We want to know moles. We're going to look at our PV equals nRT, ideal gas law. We're solving for moles. So moles will just equal PV over RT. And we just plug this in. So we have P, V, T. Now R is 8.31. We just multiply that out. That equals 11 moles. Now we don't know what the gas is, but we might be called upon to calculate the grams, and we'd have to know what the element is. We also might have to calculate how many particles that is, but we should know how to do that, going from moles of anything to grams or particles of anything. Now we get to Dalton's laws of partial pressure, and really Dalton's law makes sense, it's intuitive just like all the other ones. And he says in a mixture of gases, the total pressure is the sum of the partial pressures. So we have partial pressures that all add up for a total pressure. So pressure of total equals pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3, etc., etc. And here's a picture of John Dalton. And he really looks actually a lot like Gay-Lussac and Charles. All these guys seem to kind of look the same, except Boyle, who was rocking the cool 80s hairstyle. So if we look at this neat diagram, we have different gases in container A, B, C, and this one has a partial pressure of 100 kilopascal. This one has a partial pressure of 250 kilopascals. This one has a partial pressure of 200. Now we add up those partial pressures and we should get 550 kilopascals. That's the total. All of these are combined in the same. Now the thing is, you have to have the same container, same size container. Let's try a Dalton's law problem. A metal tank contains 3 gases. So we have 3 gases in the metal tank: oxygen, helium, and nitrogen. 3 gases here, and they all will exert a pressure. The partial pressure of the 3 gases in the tank are 200. So pressure of oxygen is 200 kPa. Pressure of nitrogen is 500 kPa, and the pressure of helium is 100 kPa. What is the total pressure? Well, this is addition, so we just have 200 plus 500 plus 100. And let me get a calculator out. 200 plus 500. Let me pause this and I'll get back to you after I calculate this. Okay, my calculator says that is 800 kilopascals. Okay. Now the last law we're going to get to is Graham's law. And here's Graham. Kind of everyone has those neckties on. And what he said is gases of lower molar mass will diffuse and effuse faster than gases of higher molar mass. So if you're big and heavy, you're not going to diffuse or effuse as quickly as those lighter ones. Diffusion, to review from biology, is really the tendency of molecules to move toward areas of lower concentration from higher concentration until the concentration is uniform throughout. So things are going to diffuse from high to low until everything is equal. Effusion is a process that occurs when a gas escapes through a tiny hole in its container. So if there's a little hole, gas will escape, and it's effusion. It's basically similar to diffusion. Let's look at the equation. Here's Graham's law right here. Graham's law says if we have a velocity, the rate of 1 over the rate of 2 equals the square root of the mass of 2 over the mass of the other one. Okay, so basically what you're doing is if we look at it, we're just looking at the square root of the masses. Everything here is based on the size, so the bigger will move slower. So the velocity or the speed or the rate is going to be dependent on the mass. Let's look at an example here. Two gases of different isotopes, thorium-232 and thorium-235. That's their masses, remember. So isotopes are the same elements with different masses because of a different number of neutrons. They're separated from each other using gaseous diffusion. So we can calculate the relative rates of diffusion of gaseous thorium trifluoride and with these isotopes. So if there's a thorium trifluoride with the molar mass of thorium-232 has 289, and the molar mass of thorium and the molar mass of thorium trifluoride containing thorium-235 would be 292. We're looking at a ratio. Let's assign some values here. Let's say mass 1 equals 289 and mass 2 equals 292. Let's figure out the speed of, so the speed of V2 is V1 square root of 289 over 292. That's mass 1 divided by mass 2. So that equals 0.99. So V2 will equal 0.99 is 0.99 times the speed of V1. Or now if we did the inverse of that, if we did the inverse, which is x to the minus 1 on your calculator, we could say V1 will equal 1.005 times the speed of V2, meaning V1, the gas V1, the smaller gas with the isotope 232 goes 1.005 times the speed or faster than V2. So really we're looking at Graham's law, and it shows that the faster one is the smaller one. So if you're small, you're lighter, you move faster, and that makes sense. If you're a big lumbering gas, you're not going to be able to move as fast.